I want you to just take a second and imagine taking a stroll through a typical city park. You hear the rustle of leaves, maybe some distant traffic, and, the constant familiar chirping of birds up in the canopy above.
Right, it's just the usual soundtrack of being outside.
Exactly. And it is so easy to process that chirping as just, well, nature's background track. But if you were to actually decode those frequencies, you would realize you are walking through this dense, highly coordinated communication network. Those birds are actually having grammatically structured conversations.
Yeah, it completely forces a reevaluation of the acoustic environment. You realize that what sounds like random vocalizations is actually the stream of specific semantic data. It's being transmitted, received, and translated in real time.
It is wild. And to understand how this works, our mission today for this deep dive is to dig into a really fascinating stack of field research notes, acoustic analyses, and published papers. All of this detailing the work of Dr. Toshitaka Suzuki.
Yes, he's an animal linguist at the University of Tokyo.
Right, and he has spent over 15 years out in the field studying this small, super common bird called the Japanese tit. And his data provides this rigorous, empirical challenge to the long-standing assumption that, humans are the only species capable of true language.
It really is a profound shift in the literature. Dr. Suzuki's field data doesn't just suggest advanced cognition in avian species.
Yeah.
It systematically dismantles the anthropocentric bias that has governed behavioral ecology for centuries.
Okay, let's unpack this. Because to fully grasp the weight of Dr. Suzuki's acoustic data, we need to look at the baseline assumptions of ethology that he was actually working against.
The historical context is crucial here. So, the prevailing scientific dogma traces all the way back to ancient Greece, Aristotle specifically.
Oh, wow, going way back.
Yeah, and Aristotle's philosophy of mind categorized human language as uniquely semantic while relegating animal vocalizations to just pure emotion.
There's noise, essentially.
Exactly. And even Charles Darwin, who, bridged so many gaps between species, he maintained this divide too. For generations, behavioral scientists operated on the assumption that an animal's call was strictly a binary indicator of its internal state, a reflex of fear or pleasure or aggression.
So under that framework, an alarm call isn't communicating a specific noun like predator. It's just the acoustic equivalent of an involuntary gasp when you get startled.
Precisely. The assumption was that the cognitive architecture required to associate a specific sound with an abstract concept and to project that to another individual was exclusively human.
But Dr. Suzuki's thousands of hours observing the Japanese tit out in Nagano Prefecture started to reveal patterns that just didn't fit that emotional reflex model at all.
No, they didn't. He actually cataloged a vocabulary of over 200 distinct vocal patterns.
Which is massive.
Yep.
But more importantly, he documented that these calls were threat-specific. So when a hawk is spotted, the birds emit a call categorized as hee-hee, and that prompts the flock to look upward and retreat into the brush.
Right. But when a snake is detected, they emit a completely different acoustic sequence. They say, ja-ja.
And that causes the flock to look downward and intensely scan the ground.
The behavioral response is highly localized to the threat. They aren't just panicking. They are executing a specific defensive strategy based on the specific acoustic signal they received.
I can hear the classical behaviorists pushing back on this, though. Couldn't ja-ja still just be an emotional reflex? Maybe it just means ground-level anxiety rather than actually functioning as the noun for snake?
That is the exact methodological hurdle Suzuki had to clear. To prove semantic meaning, he had to demonstrate that the sound ja-ja cognitively primed the bird.
Meaning what, exactly?
Meaning he had to prove the sound created a visual concept, an actual mental image of a snake in the receiver's brain before the snake was ever even seen.
But how do you empirically measure a visual concept in an animal's mind? You can't exactly hand them a survey and ask what they are picturing.
Yeah, no, exactly. What's fascinating here is how he utilized the psychological mechanism of a visual illusion to bridge that gap.
Well, this is the stick experiment. I love this.
It's so clever. So in human cognition, if you are semantically primed with a specific word, your visual cortex actively tries to map that concept onto your environment. Suzuki applied this to the Japanese tits.
But he couldn't use a rubber snake.
Right.
Right. Because then the birds would just react to the visual shape regardless of the audio cue.
Right, that would ruin the experiment. Yeah. He needed a stimulus that was visually ambiguous, something that would only be interpreted as a threat if the bird's brain was already primed to look for one.
So he used a plain wooden stick, just a small branch he found on the forest floor.
Yep. He attached a string to it, concealed a speaker nearby, and began his trials. He would play the jaw-jaw audio cue while slowly pulling the stick along a tree trunk in this smooth upward motion.
And if he is applying the visual illusion concept correctly, the expectation would be that the birds, who are primed by the snake call, would project their mental image of a snake onto that harmless piece of wood.
Which is precisely what the data showed. When the jaw-jaw call was paired with the stick's movement, the tits approached the stick with the specific, cautious, mobbing posture they reserve for actual snakes.
That is wild. And he ran this, what, hundreds of times?
Over the course of 4 years, nearly 300 times, he had to isolate every single variable.
Right, because if he played a different alarm call, like the hee-hee-hawk warning,
Yeah.
and moved the stick, the birds just ignored the stick completely. Their brains were primed to look at the sky.
Exactly. The acoustic signal has to match the visual geometry of the threat, and it goes even deeper. If he played the correct jaw-jaw snake call, but moved the stick in a jerky, unnatural motion rather than a smooth, slithering motion, the birds broke the illusion.
They just ignored it.
They ignored it entirely. The conceptual priming only worked when the specific noun was reinforced by movement consistent with that noun.
That so elegantly isolates the semantic nature of the call. It confirms jaw-jaw isn't just a reflex. It is a conceptual anchor.
It is a word.
Right. But establishing a vocabulary is just the foundation. A dictionary is not a language. True language requires compositional syntax. You need a framework that dictates how symbols combine to create new meanings.
And that jump from vocabulary to syntax is a massive cognitive leap. It requires working memory.
Because the brain has to hold the first piece of info, process the second piece, and apply an internalized rule set to extract the combined meaning. So do these birds actually build sentences?
They do, and Suzuki's data captures this syntactic processing perfectly during their mobbing behavior against a predatory bird called the bull-headed shrike, or the mozu.
Right, because one little tit alone cannot win a fight against a mozu. They need backup.
Exactly. So they use a two-part call to recruit a mob. They emit P-tsutsu-P, which acts as an alert or caution signal.
And then that is immediately followed by GG, which signals the flock to gather. So together it translates to caution, gather.
And the combination is highly effective. When Suzuki played the synthesized sentence P-tsutsu-P, GG, near a stuffed model of a mozu, the flock executed a perfectly coordinated response.
They scan for the threat, they gather around the model, and they do these wing-flicking intimidation displays.
Right. But the critical test for syntax isn't just combining sounds. It is the dependency on order.
Yeah, like in human grammar, the sequence dictates the output. For example, green light triggers a totally different cognitive response than light green.
Or how boardroom loses all its structural meaning if you reverse it to room board. The rule set is what makes it language, rather than just a sequence of noises.
So to test if the birds had a similar rule set, Suzuki manipulated the audio file. He played the exact same acoustic elements, but inverted the sequence. So he played GG, P22P, gather caution.
And the result? The birds did absolutely nothing.
Wait, nothing at all? If they were just reacting to the individual sounds independently, they should still react. They'd hear gather and they'd hear caution.
That's what you would think. But when the syntax was violated, they registered the audio as nonsensical. They didn't gather, they didn't scan for danger, they just completely ignored the broadcast.
That implies such a sophisticated level of working memory. They receive the first sound, hold it in their short-term neural buffer, receive the second sound, and run it through their syntactic algorithm.
And when the input violates that algorithm, the brain just discards the information rather than acting on it. It proves their communication system is governed by strict compositional syntax.
That raises a really fascinating question regarding cognitive flexibility. If they have this hardwired syntactic framework for their own species, how flexible is it? Can they understand other languages?
To answer that, we have to look at the broader ecology of the forest. Different species are constantly sharing overlapping territories.
Here's where it gets really interesting, because the sources detail this phenomenon of mixed species flocks. During the winter, when resources are super scarce, Japanese tits form joint flocks with another species called the coal tit.
Right. By foraging together, they share the vigilance burden. But to do that effectively, they have to navigate a heterospecific communication barrier.
Which is a fancy way of saying they have to understand each other's languages. This is the concept of bird lingo.
Yes. The acoustic analysis of the coal tit reveals a completely different vocabulary. Their specific word for gather is DD. It shares literally no phonetic similarity with the Japanese tits, Gigi.
It's like a bilingual mashup. If a human listener is fluent in two languages, their brain seamlessly bridges the gap when words are mixed. Suzuki hypothesized that the Japanese tit might be capable of a similar interspecies bilingualism.
So he engineered a hybrid acoustic sequence to test it. He took the Japanese tits semantic alert, which is pitsutsupi, and he spliced it with the Cole tits gather command, dd.
He broadcasted a synthetic bilingual sentence, caution gather.
And the Japanese tits decoded it flawlessly. They scanned for the threat and approached the speaker.
The neural implications of that are just staggering. The Japanese kit is recognizing a foreign frequency, extracting its semantic value, and slotting that foreign noun perfectly into its own native grammatical framework.
And we know for a fact they are applying their own grammar.
Right, because of the reversal test.
Exactly. When Suzuki played the hybrid sentence backward, d, pizza to p, the Japanese tits did nothing. The foreign word only triggered a response when it conformed to the Japanese tits' syntactic rules.
It demonstrates that syntax in these birds isn't just a rigid, memorized sequence of noises. It's a flexible, cognitive rule set that can process new, abstract variables.
And this interspecies networking isn't just limited to the tits either. The research extended into urban environments, observing everyday sparrows in places like Yoyogi Park in Tokyo.
Now, sparrows don't form joint foraging flocks with tits, right?
No, they occupy a completely different ecological niche, but they share the same acoustic environment.
So when Suzuki broadcast the Japanese tits hee-hee-honk warning in an area populated only by sparrows, what happened?
The sparrows immediately ceased foraging and took cover in the canopy.
They are just eavesdropping. They have adapted their neural pathways to recognize and exploit the semantic alarm systems of an entirely different species just to increase their own survivability.
It really paints the forest as this bustling, multilingual society.
Which brings us to the inevitable paradigm shift. I mean, how did the scientific community spend centuries operating under the assumption that these complex communication networks just didn't exist?
Well, the sources highlight a philosophy Dr. Suzuki developed early on, tracing back to a childhood anecdote that I think explains this perfectly.
Oh, the rhinoceros beetle story. Yeah, as a boy, he was reading this insect encyclopedia that definitively stated the rhinoceros beetle was the strongest insect in nature.
But then one afternoon, he observed a spider trap and completely consume a rhinoceros beetle in his garden.
And he took this empirical contradiction straight to his mother. He was basically trying to reconcile the written dogma with his raw observation.
And his mother's response was brilliant. She just said, then rewrite the encyclopedia.
I love that. It fundamentally shaped his methodology. It instilled the understanding that scientific consensus is always just a working model. When unbiased observation contradicts the established rules, well, the rules have to yield to nature.
If we connect this to the bigger picture, humanity's anthropocentric view of language has acted as that outdated encyclopedia. By defining language solely through the parameters of human speech, we engineered a massive blind spot.
Suzuki uses that great proverb, the frog in the well.
Right, a frog that believes the narrow walls of its well encompass the entire world, completely oblivious to the vast ocean outside. We have been sitting in a linguistic well.
And that ignorance has real consequences, especially regarding our anthropogenic impact. Because we haven't recognized the complexity of these acoustic networks, we haven't fully grasped how our physical environments disrupt them.
The acoustic data on urban noise pollution illustrates this perfectly. In urban centers, the low-frequency roar of traffic and infrastructure essentially masks the lower registers of bird calls.
So, to ensure their semantic data isn't lost in the interference, urban birds have systematically shifted their calls to higher frequencies.
But there is a trade-off. When you are forced to shout over a baseline of noise, you sacrifice acoustic nuance.
Right, and we saw a profound validation of this during the global COVID-19 lockdowns. As human mobility plummeted and cities suddenly quieted down, the birds' behavioral response was immediate.
Ornithologists analyzing the data found that the birds didn't just lower their pitch. Without the masking effect of traffic noise, the complexity of their vocalizations increased dramatically.
The acoustic bandwidth literally opened up. They could utilize the full spectrum of their vocabulary, adding all these subtle nuances and detailed syntax that had previously just been drowned out by our infrastructure.
It is a stark reminder of how deeply our mere presence dictates the bandwidth of their survival, but it also highlights the incredible adaptability of the avian brain.
So what does this all mean? Beyond the necessity of rewriting the behavioral ecology textbooks, I think it fundamentally changes how you interface with the natural world.
Echo.
The next time you walk through a park, that acoustic background track is no longer just random noise. If you can identify the jaw-jaw of a ground threat or the syntactic structure of pitsutsu pgg, you are suddenly tapping into a high-definition live broadcast of semantic data.
You transition from being a passive observer of scenery to a witness of a complex information trading society.
It demands a much higher level of respect for the cognitive lives happening parallel to our own.
And the implications of Suzuki's data are already pushing the boundaries of technology. We are now seeing projects utilizing advanced machine learning to analyze massive data sets of animal vocalizations.
Oh, that is fascinating.
Yeah, if a bird with a brain the size of a peanut is capable of compositional syntax and bilingualism, AI algorithms are going to find patterns we can't even perceive yet.
Which leaves us with a truly compelling frontier to consider. We are moving past the question of whether animals possess language.
Right. The new question is, once our machine learning models fully decode these syntaxes, what happens when we possess the technology to seamlessly synthesize their grammar and we attempt to talk back?
That is a staggering concept to process the next time you hear a bird calling from the canopy. Thank you so much for joining us on this deep dive into the hidden acoustic networks right above our heads. Keep your ears open, stay curious, and we will see you next time.